Hi VERRFers, I'm Paul Puckstellis, and I was hoping to do this live, but the prospects of Hurricane Delta and its remnants rolling through on Sunday means that I'm going to have to pre-record this video for you. And I'm coming to you today from the campus of the University of Maryland, and I'm outside the Chemistry Complex atrium to share with you a project that we're calling Chemistry in Our Garden. This is an educational project that merges chemistry, botany, art, and of course 3D printing. And the ultimate goal of this project is to give those that use and share this space a greater appreciation for the chemistry that's around them every day. My collaborators on this project are Jeff Davis and Andrea Otteson. Jeff is an organic chemist, and Andrea is a plant scientist and artist, and she does some really amazing things integrating science and art, and you can check out her website here. This project arose out of an idea Jeff had for one of his organic chemistry courses. He wanted his students to take a little different approach to advanced organic chemistry, and instead of going through and memorizing a bunch of equations and reactions, as a lot of you who've taken organic chemistry know what I'm talking about, Jeff had them working on natural products. And these are chemical compounds that are isolated directly from the environment. And because we're talking about organic molecules, these usually come from living things. And many of the natural products that we encounter in our everyday lives come from plants. This includes the PLA that many of you are probably melting in your printer right now. And even the terephthalate that is in your PETG was first characterized from extracts of the turpentine tree. Now, many natural products are also medicinal compounds, and we usually hear about these in terms of being used by indigenous peoples. And that spawned a whole field of something called ethnobotany. And it provides an important way for identifying and developing new pharmaceuticals. But plants with these medicinal compounds aren't just in, say, the Amazon rainforest. They're all around us. Having this great courtyard and garden right outside our building provided the perfect backdrop for this project. Jeff and Andrea identified all the plants that are around here, and they began brainstorming for ways to share the chemistry side with the hundreds of people that walk through this courtyard daily, at least when classes are held in person. When they hit on the idea of creating molecular sculptures of these natural products, they contacted me, and we had 3D printing in the mix. The concept behind the class was that the students would identify plants in and around the building and research any interesting or medically related compounds that might be found in those plants. We would then 3D print these and display them next to the plant. This project really started in early March, and as you might expect, we were thrown off quite a bit by the pandemic. But if you'll take a quick stroll with me through the garden, I'll show you a few of the examples of things that we put together and describe where we hope this project will go. And at the end, I'll dive more into some of the challenges that come with the 3D printing of molecular structures. So come on, let's take a walk. Well, I hope I don't make anybody too seasick as I'm going into handheld mode here. But the first molecule that we're going to encounter on our stroll here is one called betulinic acid. Now, this is a compound that's found in high concentrations of the bark of birch trees, like this river birch here. And something like 25% by weight of this birch bark is composed of betulinic acid. Now, this is a medicinal compound, so betulinic acid, as it's shown right here, here's our 3D printed model, has been shown to slow the growth of human melanoma cells. And so this is an anti-cancer agent. And also, if you make some modifications of this oxygen just right here, this becomes a potent inhibitor of HIV replication. Now, see, we've also done a few signs here for our display. And we haven't done this for all our molecules yet, but we've created these to help identify the plant, to show the molecular formula of or the chemical formula of the compound, and it has this QR code as well that takes you to the website where you can learn more about each molecule. And the idea is that this provides a unique way that you can interact both physically with the 3D printed molecule and then virtually on the website. All right, let's continue along, and I'll just show you a couple more plants and a couple more things that we printed. So the next molecule that we're going to encounter right here is cyanidin. Now, cyanidin is a pH indicator, and it's also the base molecule that's responsible for many of the bright colors that you see in fruits and vegetables. And here we're looking at the winterberry plant, and it's the cyanidin that's responsible for the bright red color of these berries. Now, the color of cyanidin, as I mentioned, it's a pH indicator, so it changes from blue to red based on the pH and other environments that it's in. It's one of the reasons why you have blueberries that are blue, and things like beets and red cabbages have their red and purple color. And it's also an antioxidant, so when people tell you to eat your blueberries because they're high in antioxidants, it's coming from this cyanidin molecule. We'll look at just one more plant and molecule, and it's right over here. And this is a really very striking plant. So this is the beautyberry. And you can see that it has these amazing purple berries on it. And there are a number of interesting molecules that have been isolated from beautyberry, and one of these is this guy right here. This is spathulinol. Here's the 3D printed molecule right up here. And spathulinol has actually been approved as a natural mosquito repellent. So if you plant a bunch of beautyberry right here, you get this striking looking plant with these crazy purple berries, and also keep the mosquitoes away. So not all of the plants for which we've made molecules for are still out. So some of them obviously come out in spring and are gone. So one of the things that we've done is for those molecules, we've have them in this space right here. So we've plan on in the winter months as well displaying these along with other molecules that have been 3D printed as part of the educational program in the Department of Chemistry and Biochemistry at the University of Maryland. These are a couple of our plant compounds. This is narcyclacine from daffodils and berberine from the barberry plant. So we've just spun everything back up with this project after being down for quite a while. And we now have 4 undergraduates. We have Fiona, Rebecca, Joshua, and Lucas that are continuing the process of cataloging, researching, and ultimately they're going to do the 3D printing of many of the molecules in our garden as possible. Now, one of the important goals of this project is also giving back. So one of the things that we are intending on doing is setting up a repository for both the information about the molecules as well as the 3D models themselves, so that if you're interested in doing something similar in your garden or in your local park, you can download these models and get started. It doesn't have to be just chemistry in our garden, it can be chemistry in your garden. We hope this project, using 3D printed sculptures, can help open up and expand the appreciation of some of the amazing things that we walk past every day. Now I'm going to transition a bit and talk a little bit about some of the challenges that I've run into when it comes to 3D printing molecular structures, and also some of the tools that I've developed to overcome these. So there are a number of challenges when it comes to 3D printing molecular models. And the first one that you run into is that when you're printing something that has a complex 3D geometry, the number of supports that you need scales with that complexity. So this isn't a huge problem with the garden project because those molecules are fairly simple. But if you're trying to print something like this DNA double helix here, you have to use tons and tons of supports in order to do this. And I'll point out that I don't actually use this slicer. I just want everyone to know that, but it's nice to be able to show the supports like this. Now, the other problem that you run into is that of scale and volume. If you take the example of bitulinic acid that I gave you, we wanted to print that at a very large scale, but we're limited by the volume of 3D printers. So, you can only print it so large if your printer will only print a certain size. So the way that we can actually overcome both of these issues is by reducing molecular complexity. So if we take a complex molecule in 3-dimensional space and now split it up into individual pieces, so this is an ATP molecule where we've split it up into 3 independent pieces where you now have a pin down here and you have a hole in this atom where that pin fits into, you can arrange these on the build plate so that you need just minimal supports to be able to print this, and then you can assemble it after the fact. And it's much faster, saves material, and works really well. So in order to do this, I developed an add-on for Blender called MolePrint3D. And this is a Blender 2.7 add-on. And before you ask, I have updated to work with Blender 2.8. But it turns out that they removed the carve solver from Blender 2.8. And there are certain things that just work a lot better with the carve solver. So I've stuck with Blender 2.7 at this point. And the idea behind this is that this provides you an interactive way of splitting up these molecular models into smaller pieces, where it'll automatically create the pins in the bonds and holes in the atoms so that you can assemble this after they've been printed. And it does a number of things, including automated model orientation, so getting your models arranged on the bed, and then also it'll do multicolor output, so you can do MMU or palette style prints. And you can get the add-on down here, and you can read more about it in a publication that I did a couple years ago already for this. And I'll just show you some examples of things that you can do with this. This isn't related to the garden project, but you can do very complex 3D prints when you're splitting things up into pieces, and you're just really limited now by assembly time. So I'm just going to run through and just show you very basically how this add-on in Blender works. Okay, so this is the MolePrint3D tool interface that you use for doing this. And we input VRML files or X3D files, and these can be output by pretty much all of the molecular visualization software that's out there these days. And I'll just zoom in on this. And this is the spethulinol that I showed you earlier. And the thing that makes this work is that the VRML 2 format uses primitives, so you have spheres and cylinders, and we know in this case that all of the atoms are going to be spheres, and we know all of the cylinders are going to be bonds. So that's one of the principles that it uses for working with this. And we do things like clean up the scene here. We can do things like add in this, for example, should be a double bond, so we can convert that into a double bond. And then we build our interaction list so it knows which cylinders and which spheres are touching each other. So we set that up, and now what we can do is start splitting this molecule up into different pieces. So as soon as we start clicking, it changes color to indicate how many different groups that we're going to have. And for this example, let's say I'll set up these and one more. And so now what we would have is two different groups. So this would be, and every place where there's a junction, it's going to put a pin. So we could do this in a whole variety of different ways, right? We could set this up to do something like this, just depending on how we wanted to print it. And it's nice to be able to have this be interactive. And just to give you an idea, you can set some of the different features. So you can set the relative size of the pins and how much play that you're going to have for the pins, etc. And you can even do things like split pins. So I won't bother showing you that, but there's a number of different features that go into this. And then we just do this set pin group and then click pin and join. And what it'll do now is it'll split this up into two objects. Here's one where it has our pins, and then we have our other one here, as you can see, that has the holes. And now we can get this into a decent orientation on the build plate if we just click floor all here. And now if we look at the direction relative to the build plate, Z is blue here, so Z is up. So this just uses convex hull method to look for the largest surface area to put down onto the build plate. And that's really all it does, but you can do complex things. You can make every single atom and every single bond its own individual object, basically just a little molecular model kit, which is kind of what we've done with some of the bigger things in the garden project. And so this is something that I very sort of seldomly update it now because it's gotten to a functional state, but I'm still looking for new features to put into this. And it has been very useful for doing these type of molecular models. Okay, that's it for me. Thanks, guys.